Hey guys, Heap here, and welcome to a 4-part introduction to binary exploitation. It will have several exercises along the way, and we will go from the very basics all the way to arbitrary code execution. Now, by no means is this going to be a complete guide. No. Binary exploitation, or pwn, as it's often referred to in CTF challenges, is a very, very deep rabbit hole. And it fascinates me because typically solutions to these challenges are very precise, elegant, and require deep and sophisticated knowledge of lower level details to pull them off. I'll cover 4 main topics that I think are key for modern day exploitation, which will hopefully help you to get your foot in the door. And the first topic that we will delve very deep into is the stack. And if you like the sound of it, then feel free to overflow the like button for the YouTube algorithm. Thank you very much. And one final note, if you don't get all the details, don't worry. Just try doing the exercises and rewatch parts that you get stuck on as you go. Good luck. So, the stack, what is it? It's a very quick and temporary storage of local variables, and it has quite a few very, very important quirks that helps us as attackers, and having full intuition of them will go a long way during exploitation. Whenever functions get called, new stack frames get built to accommodate new local variables. And whenever a function returns, the stack frame gets released. But mind you, there's nothing explicitly happening in that scenario. What really happens is that the stack pointer moves back to the previous function, and the just released data, it stays there until another function gets called and overrides it. The stack frames are not constant sized. They can override something like half of the previous data, or more, or less. Let's take a look at a single function call, shall we? On the left, we have a C code of the function, and there are several variables that get declared. Let's take a look at what happens to the stack along the way. When the main invokes check password, it builds out a ladder which contains a so-called return address. This return address will lead the processor back to the middle of main where it got invoked. Meanwhile, the first thing check password does is building a new stack frame. It is done by pushing the previous base pointer onto the stack and setting it to the current stack pointer. Dereferencing the base pointer allows us to walk between the stack frames, but it's not really needed for our purposes. And by this point, you will have probably noticed one of the quirks of the stack, and that is it grows downwards. As you can see, the return address is higher up than the stack frame pointer. This is the legacy of the old times when the address spaces used to be very, very small in a program, and it is no longer the case today, because a typical x64 user space has 128 terabytes of address space available. But it was kept this way for simplicity, and you will see very soon that it's one of the best things for an attacker. So let's just get back to the execution. The next thing that happens is our first variable being declared. It is being pushed at RPP -4. Then we have needs checking being pushed, and finally we have a space being allocated for the password. And you can probably notice that it allocates 40 bytes instead of 32. This is because the stack frame typically needs to be aligned by 16 bytes, and the compilers often rely on it to emit more optimized code. If it were unaligned, you could get further crashes in deeper function calls. And as far as the stack frame is concerned, nothing else matters in this function. Upon return, the stack pointer goes back up to the base pointer, which then gets popped. And finally, the return instruction jumps back to main, leaving this entire function behind. So assume we don't know this password right here. How could we exploit this function? Just think about it for a moment. One way to go about it would be making isValid a non-zero value and making sure that needs checking is 0 so that this branch right here gets completely skipped. User input gets read in the gets function and it reads it to the password. Now, gets is a function that is highly insecure. It reads an arbitrary amount of input and the only two ending conditions are end of file or a new line character, which is the more typical end condition. So it can read more than 32 bytes right here. It can read more than 40 bytes right here. It can, well, override these values because the stack goes downwards and these values are above the buffer. And it's really, really amazing for us because that allows us to do just what we thought of doing. So all we need to do is write 4 random bytes right here, then 4 0 bytes to set needs checking to 0, and anything non-zero like 1 to set isValid to a non-zero value. And once we submit it, we override data. Needs checking gets set to 0, isValid gets set to 49, and once we return, we get valid as the output. You can try this out on the container that I've set up. Just run these commands and basically run the container. Once it's running, try netcatting into the 8891 port and try performing the exploitation. Unfortunately, we must somehow submit a 0 bytes into the input, and which is not possible with regular input. You can walk around this by using this echo trick, and it should work. And it works, but really the most forward-looking way would be to use an industry standard framework specifically made for binary exploitation, which is pwntools. And this code, right here, we have just an if condition to either do it on a local binary or remote into the 8891 port. And the solution is actually pretty simple. We just wait until we get some input, like the enter password, and then we finish reading the entire line. And finally, we just send our input, which is right here, and then we just print the very next line. And if we just run example 1, as you can see, it runs and prints out valid. Now, there are 2 exercises that I'll leave up to you to do, and go try them out. Now, you may be wondering how to figure out how much and what needs to be overridden, because, well, you're only given binaries in the public directory. For that, we need to do a so-called reverse engineering, and it's the process of looking into binaries and figuring out how they work. For that, there are several free tools that should help you along the way. And one of them is IDA, then there's Ghidra, and then there's GDB and OBG dump that are free tools. Then there's Binary Ninja, which is paid only, but it's pretty nice, I hear. We will be using IDA throughout this series, so I'll just show you real quick how to use it. Just run it like so, and disassemble a new file. Open the executable you want to decompile. Just press OK, yes, whatever, whenever it asks, until you get to this point where analysis is complete and you have this graph view of the main function. Right here, you can see a call to check password, which we double click, And right here, we're able to see various stack offsets. If we were to just press F5, we're able to see a relatively accurate C decompilation of the code given. And I think that's enough for these exercises, and best of luck! In the next part, I'll go through solutions for the exercises, and then we will go deep into return-oriented programming, which is a very, very powerful technique. If this was helpful, then share it around with others, and don't forget, my name was Heap, yours was undefined. See ya!